Hello, everybody. I'm going to go through this a little bit quicker than the normal practice questions because the logic ends up being the same for basically all of them. Um, okay, so first and foremost, which property shows a general decrease across the periodic table? This is the key word here. So as we go, if we have our little periodic table here, and we go from left to right, from Na to Cl, what we have is energy levels of electrons are constant, they're not changing, but the number of protons is increasing. Therefore, my radius is decreasing, and everything else is going to be increasing. So electronegativity, ionization energy, and electron affinity is all going to be increasing. This is going to be pretty important because I'm going to just really start to shorten all of the explanations up because it's the same pattern over and over and over. And because of that, we're looking for something that is decreasing. And I already hit it on the radius up there. So because of that, we get atomic radii. Okie dokie, which ions are listed in order of decreasing ionic radius? So we're looking for the largest radius first. All right, so we got Mg, sodium, fluorine, and O2 minus. In other words, these are isoelectric, meaning they have equal numbers, so the electrons are equal in all of them. So if the electrons are equal in all of these, what that means is they all end up having the same number of energy levels. These all end up having 2 completed shells. So then since they all have the same number of shells, we're looking at the number of protons. So magnesium has the most number of protons. I'm doing this without a periodic table. So 9, 8, 11, and 12 protons for each of the respective ones here. So then if protons are higher, so magnesium has the most, that means the attraction between the electrons and the nucleus is stronger. So since the attraction also goes up, that means my radius will be going down. So I'm looking for, if it's going to have the highest radius, I'm looking for the one with the least number of protons. So then I end up getting B. In general, what you can always think about this as the more an ion, the higher the charge an anion has, the larger the radius, because what we have is more electrons, and those electrons start to repel. So for O2 minus here, we've added in, this has 2 additional electrons with the protons staying the same, so we get added repulsion without the nucleus being able to effectively compensate and pull those electrons back into the I guess pull the electrons in. So the radius will just start to get bigger and bigger and bigger and bigger the more electrons we add if the protons stay the same. Same idea, but reversed for a cation. So my magnesium here, the 2 plus, the higher the cation charge, so if it was 2 plus compared to 3 plus and 1 plus, if these were all equal numbers of energy levels, so if they all had 2 energy levels or 3 energy levels, the one with the higher cation charge will be the smallest. So my 3 plus ion will be the smallest because it'll have less electrons then. or more protons, however you want to think about it, depending on the situation. Which property increases with atomic number for both the alkali metals and the halogens? So I picked this question because it's worded very, very poorly. It's tricky. So which property increases with increasing number for both the alkali metals and the halogens? So what that means is, so my alkalis are lithium, sodium, potassium, rubidium, cesium, I think is the order. And then I have fluorine, chlorine, bromine, iodine, astatine. I might have one or two of these mixed up, or it really doesn't matter right now. What happens, what the trick is if the atomic number is increasing, that's a fancy way of saying the fluorine to chlorine to bromine to iodine to astatine. In other words, they're just asking us as we go down a group, so as we go down the periodic table. So which property increases with atomic number for both alkali metals and halogens? So what I'm seeing here is, as we go down the periodic table, the number of energy levels of electrons is increasing. Therefore, the radius is also going to be increasing. Which property increases? And there it is, atomic radius, just like that. If radius is going up, I know that electronegativity is going down, ionization energy is going down, and we don't necessarily need to care about melting point right now. But it also does go down for alkali metals, but not for halogens. So that's a little bit trickier. So anyways, same logic over and over. It's just at this point we're just trying to decode the words. All right, free response. Explain why the atomic radius decreases from sodium to chlorine. And they are kind enough to give us a whole data table, because IB is a generous entity. Okay, so we've got atomic radius decreases from sodium to chlorine. So we're looking at this bit here. And it does, in fact, do what they say it does, which is great. So then what we have is energy levels of electrons are constant, or what you could say is shielding electrons are constant. Both of these are fine ways to think about this. So they have the same number of shells. I'll even write that. These are all three different ways of saying the same thing. Same idea. I'm just trying to give you all the ways you could possibly say it. But, and I'll color code this, but number of protons is increasing. Or we could say the nuclear charge. Oh, I'm missing an H there. Charge is increasing. Or we could say the effective nuclear charge is increasing. Therefore, let me color code this. Let's switch to black. Therefore, let's say, what's the best way to say this? Nucleus can attract valence electrons. Oh, I almost made that a positive sign. That would have been a disaster. Can attract valence electrons more, leading to lower radius. I would say more effectively or with more force. Yeah, I'm not happy with this, how this black part is worded. Hold on here. Nucleus can attract. Oh, that's not even how you spell attract. Let's fix that right now. Nucleus can attract valence electrons more strongly. Or, yeah. That's all right. That's okay. That's not so bad. So the trick with these questions is I'm not sure. It's a 2-mark question, and I'm not sure which one of these 3 bits they're looking for in terms of the mark. So I would always, if I was in the habit, if I were you guys, I would get in the habit of always referencing the number of energy levels of electrons, the number of protons, so what's happening between those two, and then describe or explain that the nucleus now has a stronger nuclear charge, therefore it can attract them more strongly. So even though it's a 2-mark question, I would get in the habit of saying all 3 things, because we don't know what's on the mark scheme, and we're too smart not to show off this brain that we got. We work too hard to not just say everything. Prove to them you know what's going on. Okay, so same question. This was just the second part. I took it off a past paper. The ionic radius of aluminum is smaller than its atomic radius. The ionic radius of phosphorus is greater than its atomic radius. In other words, they want us to talk about phosphorus and aluminum specifically. Explain the large difference in ionic radius between aluminum and phosphorus. So they just want ionic radius. So I'm going to just scribble out atomic radius right now, so we don't make the mistake of talking about the wrong one. Aluminum forms a cation, which is aluminum 3+. And when it does that, it actually loses its 3 valence electrons, which what actually happens then is it goes from which means it lost a complete energy level. In other words, now it only has, 2 energy levels instead of 3. Phosphorus, though, on the other hand, gains 3 electrons, therefore has 3 energy levels, and I don't want to even write instead. It's got 3 energy levels of electrons, causing greater repulsion leading to a larger ionic radius. Please don't write these arrows like I'm writing them. I'm just doing it because I'm running out of room, and I write massively like a 4-year-old apparently. So it's just the idea that since aluminum's got 3 valence electrons, and since the radius this is actually a perfect time to reference this. Since the atomic radius of aluminum is large, it's not able to hold on to those 3 valence electrons with much force. So the ionization energy of aluminum is lower compared to phosphorus, where it's actually going to be higher. In other words, it's easier to remove electrons from aluminum than it is to gain due to the atomic radius. It's more energetically stable. And then the reverse process is the same for phosphorus. If we had to guess, and I know this isn't the question, if we had to guess silicon, is this a cation or an anion? That would just be a cation. And I know that because there's a huge change in atomic radius. It goes down significantly. Also, we can see this massive jump between phosphorus and silicon as well. So if the ionic radius ever gets much smaller, that means it's lost electrons. And if the ionic radius gets much larger compared to its atomic radius, that means it has gained electrons, which means it's causing greater repulsion, leading to the increase of the ionic radius. Which reaction occurs readily? Br2 and I-. So here, in order to do this, we are going to need to compare all of, so it goes F, Cl, Br, I, At. Who cares about At right now? Because it's not even on here. And who cares about F? Because it's not even on here. So what I have is, as we go down, my atomic radius is increasing. Oh, I just mashed together my E and my A. Increasing, which means the everything else is decreasing as we go down. So we're talking electron affinity, electronegativity, ionization energy. These are all going to be decreasing as well. Another thing that actually happens with these is the reactivity is also going to decrease. I'm going to try to stay away from using that word reactive or reactivity because I just don't like it. It's not descriptive, and it's a poor way to think about it, but it'll work. So anyways, what I'm seeing here is bromine has an oxidation state of 0 and iodine has an oxidation state of -1. And so do we think bromine would have the ability, the power, to be able to remove electrons from an electron-rich I-? So this is how I want us to start thinking about this. I- is electron-rich. And Br2, does it have the ability to remove an electron from I-? Because the electron affinity for bromine is greater than iodine, this will actually happen. Bromine will be able to remove that electron and reduce itself and oxidize I-. So this one will work. A good way to think about it is bromine is more reactive, if you want to think about it in terms of GCSE. And the same thing here, but it's an opposite comparison. So what I have here is Br2 in terms of electron affinity it's less than Cl-. So in other words, it doesn't have the power to remove the electron from chlorine. Chlorine is going to hold on to that extra electron more tightly with more force because the radius is smaller, which means the nucleus is able to hold on, it's able to attract that extra valence electron with more force than bromine will be able to. So because of this, we will have no reaction for number 2. So our answer would be only I. Oh God. Let's just, hold on. I just realized it looked like that said, no reaction I. No, there's a wall there. Sorry, it's a little too cramped. Describe and explain the redox reactions of Cl, Br2, and I2 with Cl-, Br-, I-. 5 marks. First of all, IB is trying to get away from these massive 5-mark questions because it's just too... It's too big. It's too big, and it's hard to figure out what exactly they want. So for me, what I would I would just show the ones that do react. I've never even seen the mark scheme for this, so you're going to listen to me struggle through this. And I doubt I would even get all the marks because I'm not sure what they want from me. So what I would do is Cl2 reacts with, don't forget the I, with Br minus and I minus. Br2 reacts with just I minus, and I2 reacts with none. And this is all because of, all due to electron affinity. So in other words, Cl2 is going to have a greater electron affinity than Br2, which will have a greater electron affinity than I2. Electron affinity, which also is the reason why we have, which explains the reactivity of these molecules as they all gain electrons. So I think this would probably get me 3 marks, because this word here tends to tell us to state any color changes, or like literally describe what we would see if these were to happen. In this one, I would say we would end up seeing a dark liquid formed, because we would be forming I2 or Br2. This would not get you the full marks. For sure it wouldn't get you the full marks, because dark liquid is not descriptive at all. You would need to say this is brown, orange, and I would call bromine, me personally, I've never seen the mark scheme for what bromine, what IB calls the color of bromine. I would call this orange. Sometimes they think I2 looks purple as well. Now I'm starting to think we'd get 4 marks. I don't know what else I would add to this answer, but what ends up happening more often than not is there's always some random mark on there that you didn't even think that they were going to want you to say. So who knows? Who knows what else is there? Maybe they want us to say the reverse. So Cl minus does not get oxidized by any of the following, Cl2, Br2, or I2. But I think this is okay. Sorry, I never had to take IB diploma chemistry, and I'm still new to it, so I don't have all of the mark schemes memorized yet. All right. Okie dokie. Write the equation for the reaction that occurs when you put a small piece of lithium is added to water. And describe 2 observations you make during the reaction. So then lithium and water, Li plus H2O. I would suggest that you memorize this just in case it comes up. It is going to be helpful. We didn't have a chance to do this yet. I promise you we will do it at some point, probably right before a break and during stoichiometry, because it's a good way to review balancing equations, and it's actually a really fun reaction, and it makes a lot of sense to do it in a lot of places. So then we end up forming LiOH plus H2, gas, aqueous, liquid, solid. Great. This looks good, right? No, Mr. Parks. It's not balanced. Oh, that's a great catch. 2, 2, 2. I know we haven't explicitly done balancing equations yet, but I know you've done it in GCSE, so you should still balance your equations. Let me double check that it's all balanced. Yes, it is. Okay, so then we need to describe two observations we would see. Here's number one. Gas is produced. It's the only gas in the whole thing. So we would for sure see some sort of gas being produced. Also, lithium is a reactive metal. So then we would end up seeing some sort of fizzing, sparks, maybe fire, popping. I would go with fire and sparks if I were you. Fizzing, they might think that you're just stating gas again. Oh, because like gas fizzes when it is coming out of the water. Think of a fizzy drink. So then that would give us 3. So then this is, write the equation for 1, describe the two observations 2, 3. And then the last one is state what additional observation could be made if potassium were used. So then Li, Na, K. As we go down, atomic radius is increasing. Therefore, ionization energy is decreasing because this is really just a redox reaction. Lithium has 0 oxidation state and then it turns to a +1. Ionization energy is decreasing and also our reactivity for metals is going to be increasing. So for potassium, oh, that's just going to look like me writing the word fork. For potassium, more vigorous fire / reaction. This is just because potassium is larger because it has more energy levels. So it doesn't hold on to that electron as strongly. So when it ionizes, it's really a net sum of all of the electron affinities and all of the ionization energies and a couple of other things that ends up causing a release of energy. It makes it all exothermic. So because the ionization energy of potassium is lower and the same general reaction is being put in, that means the net change in energy is going to be higher. Don't worry about this too much. We don't need to cover this until later in the year. But it's just more reactive because it's able to release more energy. Okay, so I've been getting a lot of questions about what's the HL question going to be like? What do I need to know? I don't know if I know any of this, blah, blah, blah. I would say this is a very representative HL question for chapter 13 or 3 or however you want to view it. So they just want us to talk about iron. Iron is number, hold on. Number 26, I think. Yep. Iron is number 26. So then what that means is it's 4s23d 3d6. So then what that gives us is up, down, up, 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 down. So then they just want us to do the electron configurations. So that's Fe neutral. Fe2 plus is when we lose the 4s electrons. Every transition metal has this state. And Fe3 plus, I know the box has shifted a little bit, is when we get the semi-stable configuration. Great. There's our 3 marks there. What is the oxidation state of iron in this complex? So we need to remember that Cn is a -1 charge, and if there's 6 of them, that means in total there's 6 minuses. So then F is equal to something -6 -4, and I'm just getting that from the charge. So in other words, Fe is +2. Here's the key. You have to have the positive in front because it's an oxidation state. You're not saying it's an ion. So if they said, what is... So yeah, here. Let's go back up here. These are ions. Oxidation states have the number in front. So you have to write the number, the positive sign in front of the 2 on this one. So this is just an algebraic equation type of thing. The only trick is remembering what the charge of the cyanide ion is. The Cn minus. Define the term ligand. A ligand is a species with lone pair electrons which can form a coordinate bond with a metal ion. Ta-da! It's a lot of words for only 1 mark, but that's what makes you higher level. You got to know all the words. Alright, so explain why the 2 iron complexes have different colors. So what I would do, number 1, remember there are 3 things that are going to impact, well there's more than 3 things, but the 3 ones that are going to come into play with this, they're both iron, so we don't need to think about did the metal cation change. So we need to look at, is the charge the same? And these are both +2s, and we know that from up here. So the charge is the same. Let's look at the geometry. So do we have the same number of ligands? Yep. So the same number of ligands, so that's not changing. So then what happens is we have different ligands. So different ligands leads to a different energy difference between d orbitals, leads to different wavelengths of light absorbed, leads to what's the word I'm looking here? Oh, different color observed. Once again, I'm not sure which one of these 3 marks they're looking for. They might just be looking for the fact that they have different ligands, therefore there's a different energy difference between the d orbitals. But why try to take shortcuts? Play it safe, tell them all they need to know and why they need to know it. Great. Good job, everybody. Good luck.